So floor integral is very simple. So we anyway we give a formal definition and then we compute some example. So let C be a curve in Rn, piecewise smooth path in Rn, and the tau is a unit tangent vector. Such a vector because at every point you assigned a tangent vector. Therefore, such correspondence will be called a vector field. So we call it this unit tangent vector field. Okay. Along C, tau only need to define over along C. So this is our C, and the tau is everywhere has a tangent vector. This is tau. Tau is changed along the point when the point go around the curve C. Okay, and we have a vector valued function f defined in C take value in Rn. This is a vector value function. The floor integral of this f along C, which the orientation tau assign an orientation of C. The direction of tau indicate which point is the starting point and which point is the end point. In the direction indicated in this picture, the starting point is here, and the end point is here. Okay, so this is give an orientation of the curve. So we say that the floor integral of this vector valued function along C, which the orientation is associated with tau, determined by tau. The floor integral of f along C, which the orientation is this integral, which is defined using the usual line integral. Okay, so this is just an abstraction of the previous work problem. Okay, note that the floor integral depends on the orientation. If we oriented the curve by a reverse direction, so in the tau shown in the picture means that the blue point is the starting point, and this is the end point. If we reverse the role of these 2 points, now this is the starting point, and this is the end point, then the tau will reverse its direction. Okay, the vector tau will reverse its direction, so the integral will change the sign. Okay, so we have this relation, that is here C plus and C minus. C plus is the direction, is the orientation of C, or maybe C plus is the curve C, which the orientation determined by tau, while C minus is the curve C, which the orientation determined by the reverse direction of tau. Okay, obviously they will their sum will be 0. Okay, the integral over C plus is the minus the integral over C minus. Okay, So this is defined in n-dimensional space. So in 3-dimensional space, when n equal to 3, this is most interesting for physics. N equal to 3, we denote x by our x. Only usually we write xy, x1, x2, x3, but we denote it by xyz. We denote x by xyz. This is more convenient. Then the ds is dx dy dz. This is also a notation. ds is a vector, is a small piece of vector. The direction in the curve at the point x, the direction of the ds here is the tangent direction. The norm of this vector, is the length of the small piece of curve near S. That is our ds. Okay, so ds is a vector. This is a vector. The component of this vector we write it by dx, dy, and dz. So if f is a vector valued function, f the component pqr, then the integral for the flow integral is p dx plus q dy plus r dz. So we usually we will often encounter such integral p dx plus q dy plus r dz. This is nothing but our flow integral. Okay, since tau is a unit vector, the tau here in the flow in the right hand side of the definition of flow integral, the tau here is a vector, so unit vector. Therefore, tau can be represented by cosine alpha, cosine beta, cosine gamma, where alpha, beta, gamma is the angle between tau and the 3 coordinate axes. So tau is cosine alpha, cosine beta, cosine gamma, and the inner product of f and tau is p cosine alpha plus q cosine beta plus r cosine gamma. Therefore, this line integral, this flow integral can also be written by p cosine alpha plus q cosine beta plus r cosine gamma. This is just the inner product of f and tau, then ds. So this is the flow integral. And in application, we sometimes encounter integral of this form. Say it's a curve, and p is a 3-variable function, and we have this integral. This integral is not a definite integral, because definite integral is an integral over an interval. Okay, this is also not a because p is a 3-variable function. 3-variable function, previously we have multiple triple integral. Okay, but this is also not a triple integral, because the domain of integration is a curve, not a Jordan domain. Okay, so this is a new type of integral, but this is a special form of flow integral. You can consider this as the flow integral we just introduced. Here, f is p0, 0. P is a real-valued function. You take two zero components, combine with p to obtain a vector-valued function f. Then you can compute the flow integral. This flow integral is what we mean by the integral of p dx. Okay. So we compute an interesting example. This is a very useful integral. We in the two-dimensional space, xy plane, we have a unit circle. That is the boundary of the unit disk. This will usually denoted by S1. Similarly, S2 is the sphere, unit sphere in three-dimensional space. Here the one here means that this is a one-dimensional object because the unit circle is a one-dimensional object. S2, the sphere, is a two-dimensional object, geometric object. Therefore, we denote it by S2. Okay, so S1 by definition is the boundary of the unit disk. And we orienting this anti-clockwise. Okay, now we computed this integral, which is of orientation, that is anti-clockwise, y dx minus x dy over x squared plus y squared. So this is a two-dimensional floor integral. Two-dimensional floor integral. So how to compute this? Floor integral is essentially line integral. So we need to take a line integral is defined using the parametrization of the curve. Therefore, we need to choose a parametrization of our circle. So we take parametrization gamma from 0 to pi to R2. That is our famous cosine t sine t. Okay, this is the parametrization of the circle. And now the derivative of this parametrization, that is the, how to say, the tangent vector. To define the floor integral, we need a tangent vector. Therefore, we need to compute the tangent vector corresponding to this parametrization, which is minus sine t cosine t. The norm of this tangent vector is 1. This is remarkable. Norm is 1. And we note also that this tangent vector coincide consistent with the orientation. This is a unit tangent vector. Therefore, our tau can be taken as this, because this vector is consistent with the orientation. Why it is consistent? Because our orientation is anti-clockwise. So, for example, at this point t is minus pi. T is pi. Sorry, t is pi. When t is pi, our derivative gives 0 minus 1. Okay, and the tangent of our curve at this point is also pointed in this direction. Therefore, our gamma, this parametrization, consistent with the orientation of the curve. If our orientation is clockwise, we will see that the direction of tau, that is our orientation, is different from the tangent vector determined by this parametrization. Okay, because if you are oriented clockwise, then the tangent vector of the curve at this point should be this vector. Reverse the gamma dot t pi, Okay, but for our orientation anti-clockwise, they are coincide. This is useful. Now, having computed the norm of the tangent vector, that is, so that we can determine the tau is the derivative of gamma. If this norm is not 1, if I remark that if the norm is not 1, then tau should be normalized. The norm is not 1, that is easy. You divide it by the norm, then you get a unit vector, a unit tangent vector. Then this unit tangent vector might be our tau, or reverse direction, it becomes tau. So tau is equal to positive and negative, depending on whether gamma and the derivative of t, tau and the derivative of t has the same direction. Both of them are tangent vector. Therefore, either they have the same direction or reverse direction. If you have reverse direction, you will take minus here. Okay. Anyway, in our case, tau is precisely gamma dot t, the derivative of gamma. So the computation goes follows. Our integral y dx minus x dy x squared plus y squared. The meaning of this integral is the floor integral. The vector field is y x squared plus y squared minus x squared plus y squared dx dy. You only need to remember ds is dx dy. This is two-dimensional. If three-dimensional, you also has dz, but now we are two-dimensional. So ds, the vector ds is dx dy. So this is ds. This is ds. Then the other coefficient, you can write it into a vector field, vector valued function, which component y over x squared plus y squared and minus x over x squared plus y squared. So the first step is to write this into a floor, the standard form of floor integral, and then using the definition of a floor integral, this can be converted into a line integral. That is, say y x squared plus y squared minus x squared plus y squared. Floor integral is the integral of the vector value function which the tau. Now our tau is gamma dot t. Or maybe I will write tau here. Then you will obtain the real valued function. The line integral of this real valued function is our floor integral by the definition. Now, this is a line integral. To compute this, we will use the parametrization. Therefore, we substituting x equal cosine t, y equal sine t inside this integral. We will obtain what? This line integral, by the definition of line integral, we just study line integral here. Where? Yes. Okay. Here. We just introduce the line integral in this formula. Of course, our integral is along a curve, say not a parametric patch gamma. But when we having proved the invariance, this is the same as the integral over the curve C. Okay, so you have in substituting by the definition of a line integral, you substituting the variable of the integrand by parametrization gamma t, multiply the norm of the corresponding tangent vector gamma dot t, then dt, definite integral. So using this definition of line integral, we have what we have. Okay, we are here. So we need to using the definition to convert this into a definite integral. upper limit and the lower limit of the definite integral is the endpoint of the domain of definition of the parameterization. Therefore, it's 0 and 2 pi. And the function here, y is sine. The y here is sine x. The y here is sine x by the parameterization, and the x squared plus y squared is 1. X squared plus y squared is 1 because cosine squared t, maybe I will write it. Cosine squared t plus sine squared t. Then minus cosine t. X is cosine t, and then cosine squared t plus sine squared t. So this is our this. We're substituting the parameterization into this part of the integral function. We obtain this. Then tau is cosine t sine t. So we write tau here. Cosine t sine t. Then dt. You should have the norm of gamma dot t dt. Our ds always is gamma dot t dt. But now in our case, the norm of gamma dot t is 1. Therefore, ds is dt. So we simply write dt here. Okay. So now this function is easy to compute. The denominator is 1, and the inner product here is sine. Oh, sorry. I make some mistake. The tau is not gamma dot t is not cosine t sine t. Gamma dot t is here minus sine t cosine t. Sorry, I make a mistake. Okay, so the tau here is not cosine t sine t. It should be. I make a mistake here. It should be minus sine t. Oh, minus sine t cosine t as given in the both red box. Okay, so this is precisely simplify the integral. It is 1. Therefore, minus 1. Therefore, the result is minus 2 pi. Okay.